Now we have finished our first module. The title is called Matrix Algebra. Our second module have a similar title. I would like to call it Matrix Calculus. You know what's our third module? I would like to call it System Differential Equations, or you can call it Matrix Differential Equations. Keep our goal in your mind. Our goal of this course is to move your knowledge in algebra, calculus, and the differential equation, or in the advanced setting of multivariable, multidimensional in the real world. When we talk about modeling, we most likely deal with a real-world application. So we need the context, the language to describe those real applications. Your autonomous vehicle will not move on a straight line as you assume in the calculus, 1 or 2, single variable calculus. If we look at the navigation and the positioning of autonomous vehicle, they move in the 3D, at least 2D. So our goal is to learn the language to solve this application problem. In the end of this module, you are going to look at GPS positioning, error calculation, and the most famous Kalman filter, so on and so forth. Let's start. Our first lesson is going to define a few analogical concepts in the multivariate calculus, such as gradient vector and the Jacobian matrix, Hessian matrix. Those are all differentiations to the function in a matrix. So don't be intimidated by the complexity of the notation. You remember the idea is the same as what you learned in the single variable calculus. I assume most of you have learned the multivariable calculus. In here we call it Cal 3, but it will always be safer to remind you those important concepts in our first lesson. Let's look at the concept of derivatives. Start from one variable. If you have a smooth curve like this, and then let's select a point, you call it x0, and we understand that in Cal 1, the derivative is the slope of this tangent line. That's the starting point of our lesson. We're going to move to the multivariable function. What's the difference? The previous function, you have only one variable x. We think this is a map between a real number x to another real number y. It's 1D to 1D mapping. The second function, you have 3 variables. Then I can call this as space in 3D. We use r to the third to represent it. And you map a point in 3D like this to the real number. Now, let me give you an example. If let this W stands for the temperature. In the space, a point in the space, you need 3 variables, x, y, z, to specify it. So give you the point, you return me the temperature at that particular point. That relationship is a function as you see here in the second line. So let's move to the geometric meaning and talk about the partial derivatives. Again, I remind you, my intention is not to teach you from scratch. It's a review. If you have no clue, that means you probably need to go back to learn this multi-variable calculus by yourself. We don't need much, by the way, but we only need the partial derivative. The picture shows you a 2D function. In general, we can call it z, which is the height in the vertical direction, equal fxy. The xy is on the horizontal plane. Like here's the x, this is the y. And the relationship is z equal x times y. This surface is called a saddle surface. Well, you know the horse's back look like this. From the head to the tail, you got a curve down like a parabola. And from the side to the other side of the stomacher, you got another curve. Well, we have some horse lovers here. You know this more than me. So that surface is called the saddle surface. So what about the derivatives? You have 2 variables. So in each curve, you can think is cut by a plane to the surface. For example, the curve here, the blue one, is cut by the surface and a plane x equals 0. That's the YOZ plane. You cut the curve, you cut the surface, you get 1 curve. Now let me cut this by another plane, a vertical plane. That plane is the y equals 0, or you can call it the XOZ plane. Then we're going to cut this red curve. In each curve, we have a tangent line. Let me draw this tangent line, the blue one here, that's a tangent line. And to the other curve, the red one, I have a tangent line, goes this way. So if you have a tangent line, you have the slope. Those the slopes are called the partial derivatives. So I will say dz, take the derivative to x. That means the y equal a constant. In our case, y equals 0. And that derivative is the same as you take a derivative of 1 variable, regard y as a constant. You take the derivative of this to x times the constant. That will be y. On the other hand, you can use this notation to take a derivative to y, then the x equal a constant. In our case, is the blue plane, x equals 0. Then you got the dy over y. Y is changing times x, which is a constant. You got x. That's how we take partial derivatives. my emphasis is not start from definition at scratch. It's to show you the geometric meaning of those partial derivatives. Another example is the parabolic surface. And this surface I can write as z equal 1 minus x squared minus y squared. You know, it just looks like a satellite dish. A satellite dish is like this shape. So if I take the x equal 1, and then to cut this plane like this direction, I cut this black curve here. Since x is a constant, I can take the derivative to y, and then it's going to be negative 2y. On the other picture, I have the y equal 2, which is a vertical plane like this, cut the surface. And then I can take the derivative to x, because y is a constant, and then equals negative 2x. That's how we calculate the partial derivatives.